Okay, chapter 2 was about vectors in R2 and R3. Chapter 3 is about vectors in general space Rn. That means the set of all vectors with n components, where n could be 2 or 3, but it could be 5 or 10. A vector in R2 is a pair AB, which is, we will be kind of often confusing points with vectors here. A comma B could either be this point, or we could be talking about the vector from the origin to that point. And in R3, point ABC, we could be talking about the vector. Usually write the vector with the square brackets here, but a triple of numbers could be a point in R3, or it could be a vector. That means the vector from the origin out to that point. Now, in R4, we can't draw pictures anymore, but we still add vectors the same way, and we still multiply scalar multiples the same way, multiplying all the components, and we add vectors by adding their components. So we still have vector addition and scalar multiplication, and even dot products, but not cross products. Okay, and remember in R2, when you add vectors, you add them head to tail. Geometrically, you add their components. A, B plus CD is A plus C comma B plus D. Algebraically and geometrically, you add them head to tail. Multiply a vector by a scalar multiple, you're just making it C times longer. If C is positive, C times longer in the opposite direction if C is negative. And in 3 dimensions, pretty much the same. In 4 and higher dimensions, we still can do scalar multiplication and vector addition algebraically. We just can't really do it geometrically, but it helps to think about R2 and R3. Okay, throughout chapter 3 we're going to be and chapter 4 we're going to be talking about subspaces of Rn. A subspace is a subset of the vectors in Rn such that if you add 2 vectors in that subspace, you're still in the subspace, or if you multiply by a scalar, you're still in the space. In other words, all linear combinations of vectors in the subset are still in the subset for it to be a subspace. So, for example, in R3, the set of all vectors of length 1 would not be, it's a subset, but it's not a subspace, because you can take a vector of length 1 and multiply it by 10, and it no longer has length 1. So, in other words, the subset of all vectors of length 1 is not a subspace because it's not closed with respect to, well, addition or scalar multiplication. You can take linear combinations of vectors in the subset and get out of it. Basically, the set of all vectors of length 1, you can identify that with a sphere of radius 1, and you can take 2 vectors lying on the sphere, that is, whose endpoints lie on the sphere, add them together and you're off the sphere, or multiply by a scalar and you're off the sphere. On the other hand, a subspace of R3 would be the xy plane, because if you take any 2 vectors in the xy plane and multiply by a scalar or add them together, you're still in the xy plane. If third component is 0, it's going to stay 0 when you add 2 vectors with third component 0, and when you multiply by a scalar. So the xy plane would be a subspace. You can't get out of it by linear combinations, i.e. scalar multiplications and vector additions. We would we'll later call that a subspace of dimension 2 of R3. So R3, we'll say, is a 3-dimensional space, and the xy plane is a 2-dimensional subspace of R3. Any line through the origin, for example, the x-axis in R3, that would also be a subspace, because you take 2 vectors in the direction of the x-axis, add them together, you're still in the direction of the x-axis, positive or negative. Multiply by a scalar, still you can't get off of that line. So we call the x-axis a line through a one-dimensional subspace of R3. They explicitly say the 0 vector has to be in any subspace but that follows automatically from this. But if you have any vector in your subspace, you can multiply it by 0, and you better not be out of the subspace. Well, you're 0 now, so that must be in it. So any subspace whatever of any space, any Rn, any subspace has to include the 0, the origin, the 0 vector of all zeros belongs to any subspace. If you don't let 0 be a member, you can't be a subspace. So basically in R3 we'll see that the origin by itself is a subspace of, we'll say, dimension 0, because add two origins together, you still got the origin, multiply by a constant, you're still the origin. So that's a 0-dimensional subspace. Any line through the origin is closed with respect to scalar multiplication and vector addition, like the x-axis, but any other line through the origin is a subspace, dimension 1 subspace. Any plane through the origin is a two-dimensional subspace, and the whole R3 is a 3-dimensional subspace. And we'll find those are the only subspaces of R3. The origin, lines through the origin, planes through the origin, and the whole subspace. Notice that a line not through the origin is not a subspace, it's a subset, but you can take two vectors whose endpoints are on that line and multiply them by scalar, add them together, and they're no longer on that line. But if the line goes through the origin, then you can't get out of it with linear combinations, but if it doesn't, you can. The homework problems in section 2, you're supposed to tell whether some of these subsets are subspaces of R2, of the plane. So your whole space is the plane, and actually the only subspaces, although we haven't proven that, are the origin by itself, any line through the origin, and the whole thing. But using the definition, you can see that, for example, this is a subspace, the set of all vectors whose first component is 0. In other words, basically the y-axis, the set of vectors 0 comma something, that is a subspace because you multiply 0 comma something by something, you're still 0 comma something, and you add two vectors whose first component is 0 together, first component is still 0. So that's a line through the origin, namely in the direction of the y-axis, and it is a subspace. Although don't just say, it's not a line through the origin, so it can't be a subspace. You have to check that linear combinations, that is, adding vectors and multiplying by scalars, you can't get out of it to prove that it's a subspace. And for example, the set of all vectors such that both components are rational numbers, is that a subspace? Well, it's certainly a subset of R2. If you add two vectors, both of which have both components rational together, they're still rational, so it is closed with respect to vector addition, but you can multiply by an irrational number and it's no longer in the subspace, so that's not a subspace, it's just a subset. And this, basically the set of all vectors x1, x2 such that x1 squared plus x2 equals 1 is not a subspace. You can just say, well, it doesn't include the origin. In other words, 0, 0, you could just check, is 0, 0 a member? If not, it's no chance of being a subspace. If it is, that doesn't necessarily mean that it's is a subspace, but you can exclude it already, and this doesn't. So 0, 0 does not satisfy that. 0 plus 0 is not equal to 1, so it can't be a subspace because it doesn't include the origin. A set of vectors in R2 such that x times y is 0, that means either x or y is 0, so that would be vectors that are parallel to either the x-axis or the y-axis. Is that a subspace? Is that subset a subspace? No, because it is closed with respect to scalar multiplication. In other words, you take any vector which has one component of the other equal to 0, multiply it by a constant, it still has one component of the other equals 0, but you can add 1, 0 and 0, 1, and they're both in the subspace, but you add them together and you get 1, 1, and that's not in the subspace. So that is not a subset, not a subspace, it's a subset. Notice that's basically the union of two subspaces. That is, the x-axis and the y-axis are both lines through the origin, so they're both subspaces. You take the union, the set of all vectors that are in either the x-axis or the y-axis, and that is not a subspace anymore. On the other hand, the intersection of two subspaces is guaranteed to be a subspace. That's your problem 31. And prove that. You take any vector that's in the intersection, that means it's in both subspaces, and take another vector that's in both subspaces and add them together. It's still in U because it was in U. Both vectors are in U, therefore they're still in U, and U is a subspace. They're both in V, therefore the sum is in V, so it's still in the intersection. And scalar multiplication also, you take any vector in the intersection, that means it's in U and V, and you multiply by a scalar, and it's still in U because U is a subspace, and it's still in V, therefore it's still in U and V. However, the union is not necessarily a subspace. For example, well, we just gave an example of the union of two subspaces, two lines to the origin. That's no longer a subspace, but the intersection of two lines to the origin, that would be just the origin, and that is a subspace. Okay, the third section gives some examples of subspaces, and one obvious example is the span of a set of vectors. So you throw in any number of vectors in Rn, and you define the span of those vectors to be all linear combinations of those vectors. In other words, anything that can be written as multiple of one vector plus multiple of the other, etc., that's a linear combination. So the set of all linear combinations of the given vectors, that is obviously a subspace. Well, it's obviously a subset, but it's also a subspace. Why? Because you take any two vectors that are both in the span, that means they're both linear combinations of these vectors. You add them together, they're still a linear combination of those vectors. You multiply by a scalar, and they're still a linear combination of those vectors. So it's almost trivially, the span of any set of vectors is automatically a subspace. In other words, the set of all linear combinations of V1 through VR is automatically a subspace because you can't get out of the set of all linear combinations by taking linear combinations. They're still linear combinations of those vectors. Another example of a subspace is the range of a matrix. That's defined as a set of all vectors that can be written as A times something. Now, as they point out here, the range is really just the span of the columns of A, because to say that a vector is in the range of A means there's some x such that AX is Y. Well, what is AX? That's first component of X times first column of A plus second component of X times second column, so forth. In other words, being in the range is the same as saying you're a linear combination of the columns of A. So the column space is exactly the same as the range of A. And since it's a span of a set of vectors, it's automatically a subspace. You can also talk about the row space. That would be the span of the rows. And that's automatically a subspace also, because span of anything is a subspace. So the column space, the space spanned by the columns, and the space spanned by the rows are both subspaces, but notice they're not necessarily even subspaces of the same R. You know, if A is not square, then the columns are all vectors in, let's say it's A is M by N, then the columns are all vectors in Rm, and the rows are all vectors in Rn, and so they're not even subspaces of the same big space. And yet we'll find out later on that they both are going to have the same dimension. Well, we're not supposed to talk about dimension yet, but you kind of know what dimension is. But that's very surprising. So the row space is the space spanned by the rows, the column space is the space spanned by the column, and that column space is also the range of the matrix A. Another important example of a subspace is the null space of a matrix A. That's a set of all vectors such that AX equals the zero vector. It's a set of solutions to AX equals 0, and that's always a subspace for any matrix A, square or not, because you take any vector in the null space and any other vector in the null space, add them together, and U plus is, let's say U and V are both in the null space. That means that AU is 0 and AV is 0. You add them together, that's still in the null space because A times U plus V is still 0. And similarly, you multiply anything in the null space by a constant. If AU equals 0, that if U is in the null space, you multiply U by any scalar, and A times the scalar times U is still 0, because you're multiplying both sides by C. So it's closed. So the subset is closed with respect to scalar multiplication and vector addition, i.e. in terms of linear combinations. You take any linear combination of vectors in the null space and you're still in the null space. You can't get out by taking linear combinations. If U and V are in the null space, that means AU is 0, AV is 0. You take any linear combination of U and V, and A of that is still 0, therefore you're still in the null space. On the other hand, if you take the set of all solutions to AX equals B, where B is not the 0 vector, that's not a subspace. It's a subset, but it's not a subspace because, for example, if AX equals B, you multiply X by 10, then A times 10X is no longer B, it's 10B. Unless B is the 0 vector, that's not the same. So you can get out by scalar multiplication or vector addition. So the set of all solutions to X equals 0 is a subspace. The set of solutions to AX equals something else is not. Now, if you have to actually find the null space of a matrix, we know it's got to be a subspace. Then how do you do that? Well, you just solve AX equals 0 the usual way. You reduce it to row echelon form, solve for x1 and x2 in terms of x3 and x4, and write out the solution in vector form like we did in chapter 1. And so you could say the null space is a set of all linear combinations of these two vectors. So it's like a three-dimensional subspace of R4 here. All of these vectors have 4 components, so there is a subspace of R4. But the null space, the set of solutions to AX equals 0, is linear combinations of these two vectors. So it's like a two-dimensional subspace of R4. A couple of problems here. They give you 3 vectors, which are defined on the previous page. They're vectors with three variables. They're vectors in R3, and they ask, is the span of these 3 vectors the entire R3? Well, if you had, let's say, I, J, and, well, do the 2 vectors I and J, where I is 1, 0, 0 and J is 0, 1, 0, the span of those 2 vectors, is that all of R3? No, it's just the XY plane. It spans something but not the whole of R3. If you take I, J, and K, then that does span all of R3. That is a set of all linear combinations of I, J, and K. Remember, I is 1, 0, 0, J is 0, 1, 0, K is 0, 0, 1. Anything in R3 can be written as a linear combination of J and K. So IJK does span R3. IJ doesn't. What about IJ and the vector 1, 1, 0? Well, no, they're 3 vectors, but they don't span all of R3 because all 3 of them have a 0/3 component. So they span something. The span of any set of vectors is a subspace, but not necessarily all of R3. Even with 3 vectors, even with 4 vectors, it might not be. It can't span all of R3 with less than 3 vectors, though. So basically, you have to determine if it's true that any vector in R3 can be written as a linear combination of these 3. That will take a little work. It says to identify the range and null space for each of the following. The n by n identity matrix, the null space, that would be the set of all vectors such that Ix equals 0, and that just means x equals 0. So the null space of the I is a zero-dimensional subspace. Null spaces and ranges are always subspaces, but what are they? Well, for the identity, the null space is just the zero vector, so it's a zero-dimensional subspace. The range, that's a set of all vectors y such that ax, there's some x such that ix equals y. Well, that's true for any, since iy equals y, anything is in the range. So the range is the entire space. The null space is just the zero vector. So the range is n-dimensional, the null space is zero-dimensional. The zero matrix, just the opposite. The null space of the zero matrix is the whole space, because 0 times any vector is 0. So the null space is the entire Rn, n-dimensional subspace, the whole space. The range is just the zero vector, because 0 is the only thing that can be written as zero matrix times something. And some interesting problems here. Verify that the null space of B is a subset of the null space of AB. How would you do that? Well, to show that something's a subset, they're both null space of anything, range of anything are automatically subspaces. But is it a subset? Well, to show that something's a subset of something else, you have to show that anything that's in the null space of B is also in the null space of AB. Well, to be in the null space of B means that B times X is 0. Well, then if B times X is 0, so is AB times X, because BX is 0 and A times 0 is 0 automatically. So anything that is a solution to BX equals 0 is also a solution to ABX equals 0. So anything that's in that subspace is in that. And I'll let you do the second part there.